Hi, we're going to start talking about radio navigation today. For this lesson, we're going to give you an overview of different modes of radio navigation. There's a lot of ground to cover here, so we need to break it up into two videos. Make sure that you watch both before coming to class. Our goals for these videos are to learn the function, the use, the limitations of the VOR, DME, and ADF radio navigation aids, and become familiar with other types of instrument navigation, including RNAV. The IFR environment is made up of highways in the skies, routes that are predicated on different kinds of radio navigational aids, or nav aids. We'll look at how to use many of these throughout this lesson so you have a firm foundation of understanding before you jump into an airplane and practice. We'll start with VOR navigation. The VOR, which stands for VHF Omnidirectional Radio Range, is a type of short-range radio navigation system that allows the aircraft that is equipped with the receiving unit to find their position with a high level of accuracy. It uses frequencies in the very high frequency, or VHF band, from 108 to 117.95 megahertz. It was developed in the United States beginning in 1937 and deployed by 1946. Though GPS-based navigation is starting to take over, the VOR is still the standard air navigation system in the world and used by both commercial and general aviation. The VOR ground station sends out two signals. The first, the master signal, is omnidirectional. That means it gets sent like a flash in all directions simultaneously. The second signal is a directional signal and is a sweeping signal. By comparing the sweeping signal with the master signal, the angle or bearing to the aircraft from the station can be determined. This line of position is called the radial from the VOR and is referenced to magnetic north. A common analogy used to describe how this works is a hypothetical lighthouse that has two lights, one that sends a bright white pulse in all directions at once every minute, and another that emits a beam that sweeps around in a circle every minute. By timing how long it is between the pulsed light and when the beam hits you, you can tell where you are in relation to the lighthouse. There are three classes of VORs that define the distance a pilot can reliably receive their signals. You can determine the class of any given VOR by referencing your chart supplement. While flying charted airways, i.e. the airways that are on your low altitude en route chart and appended with the minimum en route altitudes, you're ensured of reliable navigation signals in most cases, even if you're outside the cone of minimum coverage. Those routes have all been tested by the FAA. Pilots wishing to fly IFR off those charted routes must take careful note of the reception distances of the nav aids they plan to use, however, and take into consideration some of the limitations of the technology. In addition to distance, another limitation of VORs is line of sight, meaning you have to be at a certain altitude to receive the signal, and any terrain can get in the way of using the VOR. There are three types of VORs depicted on maps, as shown by the symbols here. The VORTAC and the VOR DME both support DME equipment. DME stands for Distance Measuring Equipment. And that equipment gives you the distance from the station. It's common in many GA aircraft. The only difference between these two is that the VORTAC also supports some military systems that you will not be using. The middle one, or plain VOR, will not give you DME information. When using VOR navigation, it is important to always tune and identify before relying on the information. The Morse code is presented on the chart so that you can follow along, and you should do so to make sure that you have the right facility tuned in. If you don't hear the code, the station is not reliable. If you're listening to a VOR DME station and there's a long 30-second pause, the DME may be working even though the VOR is not. You should also look at the course deviation indicator, or CDI, to make sure that there are no flags. The CDI consists of an omni-bearing selector that allows you to select a course at the top of the CDI, a course deviation needle, and a to from indicator. A center needle shows the radial and the aircraft is on a specific magnetic course from the station, or a course to be flown to the station. Each of the white tick marks represents 2 degrees, with full deflection occurring when you're 10 degrees off course. You'll be expected to know where all the antennas are for the radio equipment on your aircraft. The VOR antenna is the one that's shaped like a V, which is mounted on the tail in the aircraft that we fly. Your CDI will center anytime your aircraft is sitting on the selected radial. The aircraft heading, where your nose is pointed, has no effect whatsoever on the needle, only your position relative to the radial. The CDI will also have to from indicators. If you're flying the course set at the top using the OBS, they indicate whether you've passed the station or not. You will know if you're about to pass over a VOR station that you've been tracking when you get about 1 to 2 miles away, because the CDI needle will begin to swing erratically. This is known as the cone of confusion, when you're too close to the station for reliable signals. Resist the urge to chase the needle during this time. After you pass over the station, or as you pass abeam the station if you're off course, the to from flag will flip in the opposite position, and the needle will settle back to an accurate indication. It is very important to keep 3 terms clear and separate in your mind: radial, course, and heading. The radial is defined by the direction from a station. There is no such thing as a to radial. They are always from. The aircraft shown here is tracking the 210 radial. The course is the path you are trying to fly, including the direction you are traveling on that path. The aircraft shown here is tracking a course of 030 degrees. The heading of the aircraft is simply which way it is pointed. You can see that this aircraft has a heading of about 040. Using the wrong term can lead to confusion. When using a VOR for tracking a course, always set the desired course at the top of the CDI using the omni-bearing selector, or OBS. In this case, since the course is 030, we set 030 at the top. The to from indicator is indicating to, so the radial, 210 in this case, is at the bottom. Anytime the to flag is displayed, the radial is at the bottom and your course is at the top. We use whatever heading is necessary to track this course given the wind. Here our course is still 030, so we still want 030 on the top. Since we have a from flag, the radial 030 in this case is at the top. If you have a from flag, the radial is always on the top. This is really important because if you tune it the wrong way, it's possible to get reverse sensing on the needle. So remember, from top to bottom. From flag, the radial is at the top. To flag, the radial is at the bottom. Presenting VOR navigation does not lend itself very well to this format, so we'll discuss how we actually use the VORs in flight and how we can answer all the FAA written test questions in class. There is a slight chance that you will run into a question about using bearing changes to gauge your distance from the VOR. The idea is that if you turn perpendicular to the course and time how long it takes to make a 10-degree bearing change, in other words, how long it takes to get full scale deflection, then you can calculate how far it is to the station. The longer it takes, the farther you are from the station. You should work with these formulas a little just in case you get one of those questions. This is a holdover technique from the old days where radar coverage was the exception rather than the rule, and is seldom, if ever, used in real life now. You might want to be prepared, though, for the FAA test. Remember, you can always sketch the problem out on a piece of paper to estimate what the answer is. The Horizontal Situation Indicator, or HSI, works just like a regular CDI, except that it's overlaid on top of the heading indicator. This gives a pilot a very clear visual indication of the navigation situation, as the CDI is displayed in relation to the aircraft and the to from indicator literally points to the station. They usually utilize a remote compass, meaning that you don't have to manually set them to the compass yourself. Because we rely on them so much, and because even a small error can translate into a big difference in your position, we are required to check the VORs for accuracy every 30 days if we're going to use them for IFR flight. This can be done by the pilot and must be logged with the method you used to do the check, the date, where you were, any error you see, and your signature. There are 4 ways to do the check. To remember the 4 types of VOR checks allowed under FAR 91.171, remember the acronym VODGA, kind of like vodka except with a G. The first V stands for VOT. The VOT is a testing facility available on many airports that broadcasts a test signal on a frequency that you can find in your chart supplement. It's a special signal that broadcasts the same radial in all directions. When you tune and identify this frequency, turn the OBS to 180 and the needle should center plus or minus 4 degrees with a 2 flag. Remember 182, as in a Cessna 182, to help you remember this. Then twist it to 360 and you should get a centered needle, again plus or minus 4 degrees, with a from indication. You should note any error in the log. You can also select your own checkpoint on a map. You get up to 6 degrees variance with this type of check because it's harder to position the aircraft accurately over your spot. If you have dual navs, you can check one VOR against the other. That's called a dual VOR check. They should be within 4 degrees of one another. If the chart supplement indicates designated ground checkpoints on your airport, you can use that to do the check. The acceptable error in that case is again 4 degrees. Finally, the chart supplement lists some airborne checkpoints. Just like with your own checkpoint, the tolerance for those is 6 degrees. In all cases, the check must be logged before you can use it for IFR operations. This is commonly an overlooked requirement on the pre-flight inspection, so remember to look each and every time and do the next pilot a favor by performing the check even if it's not quite due yet, if you're getting close to the date. You can remember how to record the checks by remembering the acronym SPED. You need to sign it, you need the place you did it, you need the error, and then you need the date. Just remember that along with the place, you also need to use what method that it was, whether it was airborne, VOT, designated checkpoint, etc. Some aircraft are equipped with distance measuring equipment, or DME. The DME can be built into the same receiver as the VOR, or it can be a separate unit. If it's a separate unit, you'll probably have the choice of tuning the VOR frequency into the DME box, or just have the box look at one of the other navigation radios that are installed in the aircraft, and it will use that VOR for the distance. The unit in the aircraft sends out an interrogation signal in the form of a paired pulse. The ground station receives the signal and then waits for 50 microseconds and sends a pair of reply pulses back to the aircraft with a frequency difference of 63 megahertz. The aircraft DME receiver measures the time between the pulses and replies, subtracts 50, and determines the distance from the station given that the signals travel at a standard 12.359 microseconds per nautical mile. Identification is the same as the VOR, but the code only repeats every 30 seconds. Distance is slant range, so at 6,000 feet the DME will say you're 1 nautical mile from the station, even though you're directly over it. This is important to remember both in real life when flying close to the station and when taking FAA written tests. We use the DME sometimes to fly DME arcs as part of an approach. These allow you to fly a curved path at a constant radius from a nav aid and are often used to transition from the en route to the approach structure. This approach plate shows a 16 DME arc off of the Newport VOR. In this case, the 16 nautical mile DME arc starts at the 029 radial from Newport at the Lanky intersection. Lanky is an initial approach fix for this approach. It lies on Victor 182, which is defined by the 029 radial. The initial approach fix for most approaches can be found on your low altitude en route chart, and they're the point where you transition from the en route portion of your flight to the terminal portion of your flight. So to fly this, if we're following Victor 182 outbound from the Newport VOR in this direction, we fly along the 029 radial and wait until the DME shows 15.5 nautical miles and lead our turn by a half a mile. At 15.5 nautical miles we turn so we're flying perpendicular to the VOR, in this case a left-hand turn, and roll out the desired distance of 16 nautical miles. Whether you're approaching the arc from the inside or the outside, at the speeds we fly, a half a mile early should be a pretty good lead point. Then we twist your CDI so that it now shows a radial 10 degrees off your previous one. In this case, that would be the radial 019. Wait for your CDI to center, and then turn your airplane 10 degrees. Then twist your CDI another 10 degrees. In this case, that would be 009. Wait for it to center again, turn your airplane 10 degrees, and twist your CDI another 10. The result is a series of 10-degree turns with little straight segments between them. Together they form an arc. Continue this process until you have flown the arc all the way to your desired course, the final approach course here. When the final approach course appears 90 degrees off your heading, turn the plane to your final approach course, twist your CDI so that the course appears at the top of the instrument, and fly the approach. When flying a DME arc with a wind, it's important to keep a continuous mental picture of the airplane's position relative to the facility. Since the wind drift correction angle is constantly changing throughout the arc, wind orientation is important. In some cases, wind can be used in returning to the desired track. Maintaining the arc is simplified by keeping slightly inside the curve. That way, the arc is turning towards the aircraft, and if you need to re-intercept, that can be accomplished by simply holding a straight course. When outside the curve, the arc is turning away and a greater correction is required. Regardless, if you find you're drifting too far from the station, make your next turn a little bit more than 10 degrees. If you're too close to the station, hold your heading for a little longer. Pilots have lots of tricks they use to remember which way to correct. Talk to your CFII and see which tricks they'd like you to learn.